All right, so welcome everybody to either our last lecture or penultimate lecture. So we're talking about nuclear chemistry, and we had said on Monday that we have these isotopes of certain elements which are radioactive. It's just a fancy way of saying that they're unstable and they're emitting radiation from the nucleus to try and become stable. And we looked at two of the processes on Monday. We saw we had alpha emitters, which emit a stream of protons and neutrons, and also beta emitters, which emit a stream of electrons from the nucleus. The third one we want to look at today is called positron radiation. And this happens when we have an unstable proton in the nucleus, which breaks down, decomposes into a neutron and a positron particle. Now, we haven't come across positrons before. A positron is weightless like an electron, but it's positively charged. So it's kind of like the opposite of an electron. And that positron is what is ejected from the nucleus as a stream of radiation. So while we're losing a proton which had mass, we're gaining a neutron which also has mass. So with positron radiation, there's no change to the mass number. However, we are losing one of our protons, which counts towards the atomic number, and therefore counts towards the identity of the element. And so with that loss of the proton, the atomic number decreases by 1, and we're getting a new element. It's another example of transmutation, as we called it on Monday. The very identity of the isotope changes to a different element. So there are a couple of examples of isotopes which are positron emitters, which are used in medicine. For example, carbon-11 with 6 protons, making it carbon, but only 5 neutrons, therefore a mass of 11. We get a proton decomposing into a neutron and a positron particle. The mass stays the same at 11. The atomic number has now dropped down to 5 to make it a boron isotope. And we get that positron radiation given off. Some people like to use that E symbol with a plus sign on it. Some people prefer the beta symbol. I prefer the beta because normally people start to get confused with electrons if you use a lowercase e. But you will see both used depending on which textbook you're reading. We also have, for example, fluorine. Again, that proton breaking down to give a neutron and a positron particle. And there's no change in mass, but the atomic number drops down to 8, making it an atom of oxygen. Take a look at these two for a second. I'm just going to check, because I hear the faint sound of a doorbell. I'm just going to check, see if there's somebody at my front door. No, I guess it was just my daughter's TV show, whatever she's watching. So we'll look at these two. An unstable form of oxygen. You would predict it to be unstable because there's an unequal number of protons and neutrons. We said on Monday we're normally looking for equal numbers of protons and neutrons for a stable isotope in the top half of the periodic table. So that proton breaks down to give a neutron and the positron particle. And so because the neutron has mass, there's no change in the mass number. the atomic number goes down by 1, which makes it 7. And of course, that's going to be isotopes of nitrogen. Only atoms of nitrogen have 7 protons. And for nitrogen-13, again, that proton decomposing to give the neutron in the positron particle. So that mass stays the same at 13. The atomic number drops down to 6 for 6 protons. We now have an isotope of carbon. These two particular isotopes are often used for imaging in medicine to make PET scans, positron emission tomography. Often looking at the heart and looking for tumours around the heart. Fourth one we want to look at is gamma radiation. Gamma radiation is a release of energy, wave energy from an isotope which is in what we call an excited state. Kind of like when people are in an excited state, they're maybe jumping around, they're shaking, vibrating, they're so excited. And isotopes can sometimes be in that kind of state where they just have too much energy and they shake uncontrollably. And so they release electromagnetic radiation as they lose that energy and relax to a lower energy state. So for gamma radiation, we often show the unstable isotope with a little asterisk next to the chemical symbol, which is useful because when it's just pure wave energy being released, there's no change in the number of neutrons, protons, or electrons. So the mass is exactly the same as it was initially, as is the atomic number and the number of electrons. Just a pure release of radiation. But that energy of that radiation can vary according to the varying wavelength of the radiation. All radiation moves through a vacuum at the same speed, the speed of light. 3 times 10 to the power of 8 meters per second. But what does change one form of radiation to another is the frequency of that radiation. How many waves of that radiation are passing through one point in space for every second of time elapsed. So if we look at these two waveforms, this crude diagram here of mine, not much of an artist, I'm afraid. And so if you see with the first wave, we can measure the wavelength from crest to crest, or from trough to trough, basically just from any point in the wave to the exact same point when the next wave begins. That gives us the wavelength. And if the wavelength is longer, then the number of waves passing through over 1 second is lower. But as the wavelength decreases, the number of waves passing through any point in space over 1 second in time increases as wavelength decreases. And each individual wave is like an individual packet of energy, like waves crashing across the edge of a cliff. So the more waves, the more energy we have, and the more destructive the radiation becomes. So as frequency increases because of decreasing wavelength, the destructive nature of that radiation is increasing.
Yeah, gamma rays are very dangerous.
That's what you hear. So if we put it into perspective with the other forms of radiation, the longest wavelengths are things like radio waves and television waves. We get down into then microwaves as the wavelength decreases. We eventually get into the infrared region, which is just on the near range of visible light. And we have visible light itself. And then on the far range of visible light is ultraviolet light. And this is the radiation that we fear so much from the sun, the UV radiation that we're exposed to in the summer, because that's the radiation coming from the sun of the shortest wavelength and therefore the highest frequency the most destructive. But far worse than ultraviolet light are X-rays, and then worst of all, of course, are actually gamma rays. Smallest wavelength, and therefore the highest frequency. Now, to calculate the frequency, we can use Einstein's equation for the speed of light. We say that the speed of light c is equal to the wavelength multiplied by the frequency, the number of waves per second. And just as we did in experiment number 4, we turned this around and we said that the frequency is equal to the speed of light divided by the wavelength, if the wavelength has been converted into meters, just as we did in experiment 4 with the colour flame tests. Now notice that we're not going to do any example calculations on the notes here, because you won't have to do any in the exam. You just have to be aware of it, how to calculate the speed of light. But we did the lab, so we don't have to do any more calculations. It's the last week of the semester after all, and I'm trying to keep things simple. Because I'm nice, regardless what Sydney says. Okay. Now, of course, radiation is dangerous. And remember that there's no safe amount of radiation that you could be exposed to. So the safest amount of radiation is 0 radiation. Anyone who tells you different is probably standing behind a LED screen when they tell you this. Do not believe them. Now, that's not to say that radiation therapy isn't useful. It can be used to treat certain cancers, and it can be used to create images to give us warning signs, but there is a risk. Never forget that. So it's important that the patient be exposed to the absolute minimum amount of radiation possible. One way of achieving that is using electron capture. Quite simply, we take a stable isotope which isn't emitting radiation, and we bombard it with electrons. Those electrons crash into the protons in the nucleus, and the electron and proton combine each time to produce a neutron. And so we're causing, again, transmutation, a change in the identity of the isotope, because we're changing the number of protons. So we take some beryllium and bombard it with a stream of electrons. We lose a proton, but we gain a neutron, so the mass stays at 7. But the atomic number drops down to 3, making it an isotope of lithium. And sometimes these isotopes produced from the electron bombardment are radioactive themselves. Some good examples of that are things like chromium-51, bombarded with electrons to create an unstable form of vanadium. And that vanadium unleashes gamma radiation, which has been used in medicine to create images of a patient's spleen and look for trouble. Likewise, thallium-201, bombarded with electrons to produce mercury-201, as the atomic number drops by 1. That's an unstable form of mercury, one that releases gamma radiation, and that's been used in the past to monitor a patient's heart function. So if you minimize the amount of electron bombardment, you minimize the amount of radioactive sample created, and therefore minimize the amount of radiation that the patient is exposed to. That can be critical in maintaining the best chances for a patient's health. Any questions so far? We're doing okay? Almost there. I think, what time is it? I think we're going to make it. I think Friday will just be revision. So we also want to take a look at half-life and carbon dating. Half-life relies on the fact that when an isotope is unstable and radioactively decays, it actually decays one atom at a time. Like all the atoms in the same sample are lining up, waiting for their turn to radioactively decay. And so we can measure a very exact, a precise amount of time that it takes for a sample to decay 50%, what we call its half-life. A good example of that is strontium-90. It's an isotope which is unstable and radioactively decays by emitting beta radiation, a stream of electrons from the nucleus. Remember, we said there's an unstable neutron that breaks down to give a proton and an electron, and the electron is ejected from the nucleus as radiation. And so this happens one atom at a time, and it takes just over 28 years for half of the sample to radioactively decay. So starting off with 100 grams, we allow just over 28 years to pass. We've now just got 50 grams of the strontium because we've produced 50 grams of yttrium, the isotope which is produced from that decay. We allow another 28 years and 2 months to pass. We go down to just 25 grams, just 50% from the last half-life. We've now got 75 grams of the yttrium. We now allow another half-life to pass, again 50% decomposition. We go down to 12.5 grams from the original 100 gram sample of strontium. So every time that half-life elapses, half of the sample will have radioactively decayed. Now remember, we said that the amount of time the patient is exposed to radiation is critical. We want the patient to get the minimum exposure. And so this is why the half-life of an isotope used in medicine is so important. If you ever have to go in for treatment using a radioactive isotope, maybe a CAT scan or something, you'll probably find that the hospital alternates back and forth between different isotopes used. Check and verify which isotopes they're using. Find the isotope with the shortest half-life. The shorter the half-life, the shorter your exposure to radiation in the body. One of the best ones used in medicine at the moment is indium-116. It has a half-life of just 14 seconds. So if we look at a sample of indium, let's say we start with 40 grams this time. After that half-life elapses through beta emission, just 14 seconds, we're down to just 20 grams. After another half-life, 28 seconds, we're down to 10. After another 14 seconds, 42 in total, we're down to 5. 56 seconds, we're down to 2.5 grams. So more than 90% of the sample has radioactively decayed and finished emitting radiation after just 1 minute. I can hear my daughter calling me. That is critical. Other isotopes used, coming! Got me wrapped around her little finger, that girl. Other isotopes which are commonly used, like thallium, have a half-life of a couple of minutes. And that means a much longer amount of exposure to radiation if the isotope being used has a longer half-life. Find out which one is used, which one is a shorter half-life, and insist on getting your therapy on the day with the shorter half-life. Okay, let's take a quick break and I'll find out what my daughter's emergency is. What is it, Christina? What do you need? 1 second, sweetie. Because it's the wrong CD.